Previously on Overdramatic Chem Lab.
What did you do? What did you do?
Look, there's no one else to blame but yourself.
Always label our flask.
You did this. No, it's on you. What?
Oh,
Are you certain? That's pretty risky. You think it'll work?
So let me get the solution ready. I'll get the burette set up.
You relax. There's a lot riding on this.
yes. Please tell me you got that.
Ugh, this can't happen again.
And now, back to Overdramatic Chem Lab.
Thank you. Anyway, welcome back. Hey, remember last time we talked about titrations and we talked about neutralization reactions. We said that there's a point called the equivalence point in which the hydrogen ion concentration is equal to the hydroxide ion concentration. But when we did our titration of a weak acid with a strong base, we found that that equivalence point was above where we might normally think it would be. We would normally think equivalence neutral, right? We'd think it would be around 7, but the equivalence point was higher than that. And I told you it had to do with the salt that was being produced from this reaction and how it has basicity. Let me show you what I mean. These 3 beakers contain distilled water and the same indicator in each one. That indicator is called bromothymol blue. Now remember, we said that indicators are compounds that will change color depending on what situation they're in. If they're in an acid solution, they'll change to one color, or if they're in a basic solution, it'll be another. We used an indicator called phenolphthalein in our previous titration in the last video, and phenolphthalein in a basic environment gives us that pretty pink color that we saw. Bromothymol blue gives us a yellow color when it's in an acid solution, and a blue color when it's in a basic solution. And when it's in a solution that's neutral, you guessed it, yellow and blue make green. Now what I haven't told you is that there are 3 different types of salt in each of these beakers. This one right here in the middle, this one is our classic sodium chloride. We see that it produces a neutral solution. But another type of salt that we call ammonium chloride produces an acidic solution. And the one that we used in the last video with our titration is called sodium acetate. And as you can see, it produces a basic solution. So how do we know if a salt will produce an acidic solution, or a basic solution, or a neutral solution? Whether or not a salt produces an acid solution or a basic solution has to do with something called salt hydrolysis. So what happens in salt hydrolysis? Well, it may be that the anion portion or the negative portion of that salt will accept hydrogen ion from H2O and result in a basic solution. Or it may be that the cation, the positive portion of that salt, will donate hydrogen ion to water, thus resulting in an acidic solution. The kind of solution depends on the strength of that conjugate base or conjugate acid. Now let's look at the examples of sodium acetate that we used earlier and ammonium chloride and see why they make the solutions that they make. First, the sodium acetate. I've rearranged this, by the way, to put the sodium on front. Sodium acetate dissociates in water to form sodium ion and the acetate ion. The sodium ion is too weak to react with water on its own. We'll get to that in a second. But the acetate ion will. The acetate ion will accept a proton, a hydrogen ion from water, to yield undissociated acetic acid, that's why it's not acidic, and hydroxide ion. By virtue of the fact that when we put sodium acetate in water and it produces hydroxide ions, that means sodium acetate is a basic salt. You get it? And that's why in our titration, our equivalence point was well above 7, closer to the 8.5 range, because that salt was basic, adding a little more basicity to the solution. What about ammonium chloride? Now ammonium chloride, when it gets into water, dissociates to form the ammonium ion and the chloride ion. The chloride ion is too weak to react with water. Again, give me just a minute. But the ammonium ion will react with water. Ammonium ion will donate a proton, a hydrogen ion, to water and yield ammonia and hydronium ion. By virtue of the fact that when you put ammonium chloride in water, it produces hydronium ions, ammonium chloride is an acidic salt. So is there a way we can know for certain what it's going to be? Is it going to be acidic or basic? Are there some rules? You betcha. Let's start by talking about strong acids. Strong acids produce conjugate bases that are too weak to hydrolyze water. So I've written them down. There's 6 of them that we should be familiar with. Hydrochloric acid, hydrobromic acid, hydroiodic acid. By the way, notice those 3 are halogens. The only halogenated acid that's not strong is hydrofluoric acid. Okay? Hydrofluoric is a weak acid. Let's continue. Nitric acid, perchloric acid, and sulfuric acid. Now you might be wondering, why did you write the anion portion of those in green? Because the anion portion of those, if you see that anion in a salt, it has nothing to contribute in the way of pH. It's simply a neutral ion. For strong bases, it's the same result. Strong bases produce conjugate acids that are too weak to hydrolyze water. What are the strong bases? Well, there's a real easy way to remember. If you attach a hydroxide to a group 1 metal or the lower group 2 metals, you're going to have a strong base. The reason why I've written these cations in green, same reason why I did the ones for the strong acids. Because if those cations are involved, they will contribute nothing in the way of pH. They'll just be neutral ions. So you remember I had sodium chloride in one of those beakers, and it was green, it was neutral. Here's why. Sodium and chloride, when they get together, it's all neutral. There's nothing in the way of acidity or basicity, and so because of it, that solution is just plain neutral. Therefore, if it's not in this list, it's going to be a weak acid. And a weak acid will produce an anion that is a strong enough conjugate base to hydrolyze water, like we did earlier with the acetate ion. So if it's a base and it's not in this list, it's a weak base. And those bases produce cations that are strong enough conjugate acids to donate a proton to water and produce an acidic solution, like we did with ammonium chloride earlier, where ammonium hydrolyzed water to produce hydronium ions. Sometimes there are situations in which we don't want huge fluctuations in pH. In your body, for example, you don't want your blood fluctuating wildly in its pH or your stomach acid such that it can't even digest your food. Because of that, your body will produce buffers. And we do this in the chemistry world as well. Buffer solutions are when you have a combination of a weak acid and its conjugate base, or a combination of a weak base and its conjugate acid. So how does it work? Let's do an example. Let's say we're putting together a 0.1 molar solution of hydrofluoric acid and a 0.1 molar solution of sodium fluoride. The hydrofluoric acid will produce hydrogen ions for us, and the sodium fluoride will produce fluoride ions. Now, fluoride is the conjugate base of hydrofluoric acid. So we have this equilibrium system right here. Now let's see what happens if we add an acid or a base to this system. But hey, we have to remember Le Chatelier's principle. When we add acid to the system, it's sort of like we're adding product. The hydrogen ions of that acid are going to cause this reaction to shift to the left and form more hydrofluoric acid by combining the acid with the fluoride ion. However, if we add a base to the system, the OH ions in that base will react with the hydrogen ions and produce water, thus neutralizing or taking away the hydrogen ion. What happens when you take away product? The reaction shifts to the right. And so that's how a buffer keeps things nice and balanced. By the way, a buffer capacity is the amount that buffer can take while still keeping a nice narrow range of pH. Now when you're making a buffer, it's important to have equal concentrations of the weak acid and conjugate base or the weak base and conjugate acid. And usually you want that combination to be as close to your desired pH as possible. And the cool thing is, if there's a desired zone for your pH that you want, you can choose a buffer system based on that pH. So I have a quick little assignment for you. This is sodium bromide, rubidium acetate, and ammonium nitrate. I want you to identify each salt, whether or not it's acidic, neutral, or basic. Okay? Go get it. That's all the time we have for today. Today we talked about salt hydrolysis, how anions from weak acids can cause basic solutions, and how cations from weak bases can cause acidic solutions. We also talk about the strong acids and strong bases to watch out for when we have those anions and cations that are too neutral to do anything. Finally, we talked about buffer solutions, how you can have a combination of a weak acid and its conjugate base, or a weak base and its conjugate acid, to keep your pH in a nice, narrow range. Look at that, another chapter in the books. Can you believe it? You guys are doing awesome. If there's any way I can help you, just let me know. Give me an email and I'll be happy to do it. Until next time, God bless you.